desperately needed to have recovered. But okay, how or why? Or, all you ever do is like share success stories. You never talk about what it is. And I've sort of had that comment from people. So I thought I'd spend a minute just to sort of explain, because it's an interesting fact that I never designed Spinrite for data recovery. That wasn't what it was for. And
that's why I always call it the best hard drive maintenance utility.
Right. And it sort of had a maintenance mode, but even that was sort of a side effect. So the way Spinrite began was when it was actually generated by my noticing that there was an old style servo-based hard drive that actually a girlfriend of mine had all of her company's bookkeeping on, years of financial records, and it failed. And she was desperate to have this data back. And so I said, okay, I'll take a look at it. And this was one of those big 5¼ inch, full height, full width, really heavy servo-based drives. And I don't know what inspired me to do this, but I guess I was desperate. But I lifted one end of the drive up, and then it worked.
That's bizarre.
And I knew why, because
all the bits were rolling down to one side.
That they were loose. That's exactly right, Leo. They needed to sort of shuffle around down there and reorganize themselves.
They were all sliding to the end.
There was something known as tower drift, where a hard drive would have a servo platter, which one of the heads would read. That told it where the tracks were, and then all the other heads essentially got their positioning information just physically, because they were connected to the same mechanism. And what would happen, though, over time, just due to mechanical wear and tear, heating and cooling the drive up every morning and evening, is that sometimes the head that was furthest away would go off track. That is, it would stop being able to find the sector headers that were originally written when the drive was low-level formatted. And so what happened when I lifted one end of the drive up about an inch is that put some gravitational bias into the side-to-side motion of the heads. It literally pulled the heads toward the center of the platters, because gravity created a bias, and now we were able to find the sector headers.
Wow.
So what
I realized... You knew that? I mean, you just kind of knew that in your head?
Yeah, well, I'm an engineer, so I understood that.
Wow.
So then what I knew I had to do was I had to refresh the low-level format of the drive and essentially migrate the sector headers back to their new position that they would have when the drive was level again. So I quickly wrote a program which read a track, low-level formatted that track, and then wrote it back. And the act of doing that, that was while the drive was elevated, while it was able to find its sectors. And then I ran through that process. Then I lowered the drive about a quarter of the way and did it again, and lowered it another quarter of the way and did it again, and the final quarter of the way and did it again, and then horizontal and did it again.
Wow.
And so what that did was, with every quarter of an inch of lowering, the tracks were actually moving back out to where they would naturally be, but by low-level formatting the entire drive each time, I was pulling the headers with me. I was bringing them back into alignment, and it fixed the drive. So it was not long after that I stumbled upon the idea, or I did something called spin test and spin time when I was writing the InfoWorld column. These were very short programs where a little bit of basic with a hex with the program itself in data statements of hex at the end. And so the program would just poke the data into memory and then jump to it. And that allowed me to deliver in a printed page. It allowed me to deliver assembly code. And spin test and spin time were simple algorithms which just read sector 1 over and over and over and checked to see how long it took. And by doing some math, it was also doing like sector 1 and sector 2, sector 1 and sector 3, and so forth. Then doing some math, I could figure out what the interleave of the drive was. And what I and many hundreds of people who use these little pieces of freeware discovered was that the interleaves were wrong. The drives at that era, MFM drives, had 17 sectors per track. And the computer could not read sector 1 and sector 2 and sector 3 sequentially. It was only able to read a sector at a time, so it would read sector 1. And then after reading it, the controller would transfer it into RAM, and then the computer would ask for sector 2. Well, the problem is sector 2, if just even the first little tiny bit of sector 2 had started to go past the head, we had to wait for it to come all the way around again to get sector 2. Then we would do that. And then by the time we got to ask for sector 3, it had already started to go past the head. So again, we had to go all the way around. So this problem was well understood. IBM in the XT, they set the so-called interleave to 6 so that you'd have sector 1 and then 6 physical sectors upstream would be logical sector 2. So remember that the physical sectors are the actual physical location around the track, but each one of those sectors has a header that declares I am logical sector 1, 2, 3, 4, and so forth. So if the interleave was 1 to 1, then that would mean that the physical and logical numbering was identical. But if it was like 1 to 2, that would mean that every other physical sector was logically sequential. So you'd have sector 1, and then, I don't know, like sector 6, and then sector 2, and then sector 7, and then sector 3, and then sector 8, and so forth. So the idea that would be with an interleave of 2 to 1. XT shipped it with an interleave of 6 to 1, which meant that no matter, essentially that gave the computer ample time to read in sector 1, digest it, and decide it wants sector 2. And by that point, instead of sector 2 already just having passed by, it would still be out in front, coming toward the head. So that's much better than them having it, just underneath the head or leaving. It would still be on its way in. So what that would mean is, with an interleave of 6 to 1, you could get every 6th sector in a single revolution, or that reading a 17-sector track took 6 revolutions because you were only getting every 6th one each time. Well, the clones, the famous WD-1003 controller that all of the clone computers, the IBM PC XT clones used, the Western Digital controller had an interleave of 3 to 1. And I'm sure that some engineer at WD thought they were being really clever. Maybe they were running in an AT, like in a faster machine. I never understood why WD used 3-to-1, except that it made them twice as fast as IBM. That is, for if you use their controller with an interleave of 3-to-1, it would take 3 revolutions of the drive to read the whole track rather than 6. Unless that particular clone that you put that Western Digital controller in couldn't handle 3-to-1, which was always the case. It turns out all of the clones that everyone was using needed 4-to-1. And in fact, 3-to-1 was the worst possible interleave, because that meant that when the computer asked for the next sector, it was standing on it. It wasn't just in front of it. That sector wasn't just in front of it. It was on it. So if the disk was interleaved at 3-to-1, it took 17 revolutions to read the entire 17-sector track, because you were only getting 1 sector per revolution. It was awful, and the whole world was putting up with that. That nobody understood this. But I understood that's what was going on. The only way to fix this, after you're using your computer and you've got data, and remember, the only other backup we had was floppies. And so, people used to if you had to back up your 20 megabyte or 30 megabyte drive on diskettes, that was something you really
Did we do
put
that?
off.
Did we really?
Oh, yeah.
Oh,
we
God.
did. Remember stacks of disks? You just put one in after another. And, of course, floppies are so unreliable that you had no real guarantee that your backup was going to be usable if you ever did need it. But so the only recourse someone would have would be to back up their whole drive and then re-low-level format because it's the low-level formatting time is when you set the physical location of the sectors. And you could override with some commands. You did G = C800:5. C800 was the segment in memory, :5 was the offset of the starting address of WD's interactive sort of command line tool to do this. And then you could give some commands and it would low-level format. And you could say, I want an interleave of 4, which was fabulous, except you couldn't do it with data on your drive. So then you'd have to back up the drive, pray that your floppy backup was good, re-low-level format the drive, and then put everything back. Unless you got a copy of Spinrite. Because what I realized from my experience low-level formatting that 5¼ full-size drive was there was a command that allowed you to low-level format a track, just one. And that meant that I could incrementally low-level format a whole hard drive by doing it one track at a time. I would read the track, interleaved it, whatever it was, then low-level format it at the proper interleave, and then put the data back, and then go to the next track. If people did that, their computer would go from reading a track in 17 revolutions. This is all the clones in the industry, like virtually all the computers, took 17 revs to read a track. After running Spinrite, it was 4. So that was a 425% improvement in speed. I mean, you could feel that. I mean, the computer just booted like, whoa, holy. I mean, people were amazed. The problem was that there were defects on these drives, and manufacturers were supposed to note the location of the defects at the time that the drive was low-level formatted. Many of them didn't. But more importantly, what I'm doing when I'm changing the low-level format is I'm physically relocating the sectors to different positions. But that means that if there was a defective sector in a certain location, like sector 5, that logical sector 5 that might be marked in the file system as do not use, that becomes logical sector 10, for example, if the interleave changes, meaning that the defects are going to appear in different sectors of the file system if I change the interleave. So that was sobering, because that meant if I was going to do this, and our listeners now know, having just heard about what I've done in Squirrel to make sure that the code is secure, I'm very methodical. I'm going to do it right. So this meant that I needed to perform defect analysis to make sure that it was safe to put what was a good sector's data in a different physical location that may not have been marked out by the manufacturer, and essentially the defects were moving because I was moving the sectors around. But the other thing that happened is, if I was going to do a low-level format, we know that the one thing a low-level format does is wipe out what's on the track. It just plows a new data zone for the data to be laid down. The head is turned on, and it wipes out what's there. Well, that meant it was also incumbent upon me, who insists on doing as perfect a job as humanly possible, to make sure I have read the data that is there. That is, to recover what is there no matter what, because once I low-level format, it's gone. So what I did way back at the beginning, like 23 years ago, when I wrote Spinrite version 1, was I built in really robust data recovery technology. I mean, I did everything I could imagine. Back then, we often had stepper positioning, sort of dead reckoning positioners, where it was just a stepper motor that operated in notches, and it had a rack and pinion that moved the head out to the proper location. But it was just that mechanical system that decided where the head came to rest. There was no servo back then. That was only on the really high-end drive. The one that everyone used, I like the famous Seagate ST225. That was a 20 megabyte drive, and it just had a steel tape wound around a round hub on the stepper motor, and that steel tape positioned the head. So I needed to, in order to make sure that I got all the data that was there, if I had a problem reading the sector, I would do things like step out in one direction, then come back and try it again, then step in the other direction a different distance and come back. And in fact, I have a random number generator. There's always been one in Spinrite to choose a random distance to go away in order to come in at a different arrival velocity and profile, in order to get the head in a slightly different position, maybe to coerce the drive to give it to me one last time. I just need it one more time. And so all of that is in there. And there's even technology where if I absolutely finally am unable to get a sector to be read completely correctly, then there's a way for Spinrite to say, well, give me what you've got. And because it turns out that there was some benefit to the give me the best you can do. For example, a sector, you might have a sector that was in a file system where there's only a few entries at the beginning of that sector to subdirectories. Yet later in the sector, where there's not even anything that matters, is where the defect is. Yet the drive won't give you the sector because it says, no, I can't read it perfectly. Well, it turns out there's not actually any data there in this case, but being unable to read that sector prevents you from following those two subdirectories, which could be huge, could contain all of your database data or all of anything. And so this is one of the keys to the miracles Spinrite seems to perform, is this give me the best you can turns out to be incredibly valuable. And so anyway, back then, and all of this technology I've managed to carry forward and keep alive over the decades, back then I built the most robust data recovery I knew how to build. I mean, it does incredible tricks to get the data back, which is why it so often succeeds. And when all of that was done, when I had the data, I would then fix the low-level format and then go to the next sector. And as a consequence, Spinrite sped people's drives up. Well, the other thing it did was it recalibrated them. It was a version of that lowering the drive a quarter inch each time and doing it again. And that was where the preventive maintenance part came in. Because as your tracks are migrating over time, this migration caused by mechanical wear and tear, just the mechanical wear, and the fact that you're heating it up and cooling it down in this daily cycle, the tracks drift a little bit over time. If you run Spinrite before you can no longer read them, it rewrites them it reads them even though they're a little bit off track, but when it rewrites them, it puts them directly under where the head is now to essentially realign the data. And so it might have a hard time recovering it, but once it rewrites it, now it can read it. And the same is now true with error correction. Notice that these defects, if the tracks are migrating, the defects in the surface are not. They're staying still. But what that means is they're effectively moving relative to the tracks. So you might have had a defect that was in between tracks and not causing a problem, which migrates into a track because the track has migrated into it, essentially. And similarly, other defects might leave. So there's a lot more going on for good and bad inside these drives. A lot of this turns out to still be useful today. Interleave, that disappeared years ago, and I think it was with Spinrite 5 that I actually took that code out. It just wasn't useful any longer because all computers and drives got smart and were able to handle reading every sector of the track in a single revolution. They were all one-to-one interleave, so that went away. But all of that legacy, excruciating reformatting, data recovery, and rewriting technology, that has lived on and has ended up being Spinrite's legacy. It will almost always succeed in getting your data back. And so that's what Spinrite does and sort of why it's been doing it for so many years now.
Very awesome. You have a whole page on the website, don't you, that explains how Spinrite works. This is in more detail than that.
Yeah.
I don't think we'd ever really heard about the tilting hard drive exploit and the like.
Always like to bring some new details in.
We will talk about border gateway protocol, big iron, routing tables.
Routing tables.
And what can go wrong? What could possibly go wrong?